So next we'll talk about some more properties of determinants. And we'll start with Cramer's rule. So we're going to assume we have an invertible n by n matrix. For any vector b in Rn, the unique solution x of ax equal to b is given by this formula, x sub I equal to the determinant of a sub I of b divided by the determinant of a, where this a sub I of b is found by replacing the ith column of a with the vector of b. So depending on the size of the coefficient matrix, we'll have one extra determinant. So if the coefficient matrix is a 2 by 2, we'll be taking 3 determinants. If the coefficient matrix is 3 by 3, we'll be taking 4 determinants. So for example, we'll use Cramer's rule to solve this system. Since we have 2 equations and 2 variables, we're going to have 3 determinants. So the first of these is the determinant of A, which is just the coefficients, 2, 3, 8, minus 2. So when we calculate this, 2 times negative 2 is negative 4, minus 8 times 3, which is 24. So I have minus 28. So that's the first of 3. The second one is the determinant of a sub 1 of b. So this comes by replacing the first column with the constants, what the equations are equal to. In this case, 1 and 2. And then we'll take this determinant. 1 times negative 2 is negative 2, minus 3 times 2 is 6, so I get negative 8. The third determinant, it will be a sub 2 of b. So this time, the first column will be left alone, but we'll replace the second column with the constant vector. 2 times 2 is 4, minus 8 times 1 is 8. So this is negative 4. So my actual solution will be the determinant of a sub 1 over the determinant of a, comma, determinant of a sub 2 over the determinant of a. Reducing this will give us 2 over 7, comma 1 over 7. Problems like this is where Cramer's rule comes in handy. If you were solving this by hand using matrices or any other method, you would encounter fractions. However, Cramer's rule eliminates us ever having to deal with fractions. Here's another example. So this one has 3 variables, so we're going to be dealing with 4 determinants. So the first one is going to be the determinant of A, which comes from the coefficients. When you're forming this, make sure you watch out for where your zeros are. The first equation has a 2x1, 1x2, 0x3. The second equation, minus 3x1, 0x2, 1x3. The third equation, 0x1, 1x2, 2x3. I'm going to go down this first row to find this determinant. So that gives me 2 times the determinant of. We'll delete the first row and the first column. 0, 1, 1, 2. We subtract the second entry. Then we'll delete the first row and the second column. Minus 3, 1, 0, 2. The last entry is a 0, so we'll ignore that. I have 2 times 0 minus 1, minus 1 times negative 6 minus 0. So this gives me negative 2 plus 6, which is 4. So this is the first of 4 determinants. The next one will be the determinant of a sub 1 of b. So instead of the first column, I'll write 7, -8, -3. The second and third column will stay what they originally were in the matrix A. Once again, I'm going to go down the first row. 7 times, if I delete the first row and first column, I'm left with 0, 1, 1, 2. Minus 1 times, deleting the first row and the second column. -8, -3, 1, 2. Once again, the last entry is a 0, so I won't have to be concerned with it. 0 minus 1. Minus 1 times -8 times 2 is -16, minus -3, so plus 3. This gives -7 plus 13, which is 6. The next determinant I need is a sub 2 of b. So the first column will be back to what it originally was, 2, -3, 0. The second column will now be the constants, 7, -8, -3. And the third column isn't changing, 0, 1, 2. Once again, going down the first row, I have 2 times. If you delete the first row and first column, you'll be left with -8, 1, -3, 2. We subtract the second entry, deleting that row and column. I'm left with -3, 1, 0, 2. This gives me 2, -16 plus 3, minus 7 times -6 minus 0. 2 times -13 is -26. -7 times -6 would be positive 42. This gives us 16. Finally, we'll find the determinant of a sub 3 of b. This time, my first column is the same as it was originally. My second column was the same as it was originally. And the third column will be the constant vectors, 7, -8, -3. Since I no longer have a 0 in the first row, I'll use the first column. Deleting the first row and first column leaves me with 0, -8, 1, minus 3. I subtract the next entry, so minus -3, be plus 3. And I'm left with 1, 7, 1, -3. And once again, we'll ignore the 0, since adding 0 doesn't change anything. The first determinant would be 0 minus -8, plus 3 times -3 minus 7. So this is 16, and then 3 times -10 would be minus 30. So this would be minus 14. So my final answer is the determinant of a sub 1 over the determinant of a, the determinant of a sub 2 over the determinant of a, and the determinant of a sub 3 over the determinant of a. We can reduce this. We'll get 3 over 2, comma 4, comma -7 over 2. So this method for solving systems of equations can be used to help us find a missing value and to determine when a solution exists. So in electrical engineering and control theory, we often have a differential equation which can be converted into a system of linear equations, and the coefficients often involve a parameter. So for example, here's a linear system, and we want to find the values of the parameter for which the system has a unique solution, and then we'll describe the solution. So let's start with finding the determinant of A. Well, if I look at the coefficients of x1 and x2, I have an s minus 2s, 3, and 6s. So 6s squared minus negative 6s. So plus 6s. So the solution will occur and be unique whenever this is not equal to 0, since it has to go on the bottom of the fraction. So if this is not equal to 0, s is not equal to 0, and s is not equal to negative 1. So that's when the solution is unique. The second part of this wants us to describe the solution. So let's find the determinant of a sub 1. So this time, the first column will be the negative 1, 4. The second column is still negative 2s and 6s. This gives us negative 6s minus 8s, minus negative 8s, so plus 8s. The determinant of a sub 2. This time the first column will still be the s and the 3. My second column will be negative 1 and 4. So my determinant, 4s minus negative 3. So my solution, the determinant of a sub 1, which is 2s, over determinant of a, 6s squared plus 6s, comma, determinant of a sub 2 over the determinant of a. And we can reduce this if you want to. I will not do that here, but in general this can be reduced.